Going on, everybody? It's Mr. Gustin. I'm not in the classroom. I'm not in a conference room. Today, I'm in a physics storeroom. I've been banished to the closet. I'm like the Harry Potter of physics teachers here. Doesn't matter. Today, we're doing specific heat. By definition, specific heat is the ability for an object to transfer, or basically, how much energy is required to change the temperature of an object if we have that object as 1 gram. Okay, so it's a kind of a specific heat, specific value for specific materials, but it is an identifying value that we can use to identify unknown materials. So I've got a practice problem for you. We'll model it, and then we'll do the problem, okay? So basically, here's what we got. I got a piece of metal, and that piece of metal is 125 grams. It's sitting in some hot water, and that hot water, you can see, ooh, it's so hot, is on the hot plate. All right, it says this bath is 310 Kelvin. Now, at some point, I take that metal out and I place it into an insulated cup or an insulated piece or an insulated sample of water. All right, that water has an initial temperature, it says, of 293 degrees Kelvin, but this hot metal that is dissipating its heat into the water will have a chance to equilibrate with the water. And when finally all of that heat from the metal warms up the water, we end up with a final temperature of both for 297 degrees. This is kind of key happening here, right? Like this metal is warmed up because of this water. When I place it in a new sample, these two objects will eventually reach the same temperature. They might feel different, but they'll reach the same temperature. So they have different starting temperatures, but the same ending temperature because they're in the same space. All right? The question here is, given all that information, given that whole experiment, what is the specific heat of this metal? And then perhaps we can even identify what that metal is. All right? This is the setup of the experiment. I'm going to go ahead, though, now and do the math. Now, specific heat, anytime we're trying to solve a problem, it is completely predicated on the fact that energy is conserved, right? So the heat that is gained, I should probably do capital Q, our equation is capital Q. The heat gained by the water is equal to the heat lost by the metal. So if we think back to our model, the metal is hot, I put it in the water, it's going to lose heat to the water. When it loses heat to the water, the heat that is lost to the water is equal to the heat that is gained by the water. And that's got to make sense, right? Like, where did the heat come from to increase this temperature? It came from the metal. So the metal lost the heat, the water gained the heat. This is what it looks like. Okay, so on the side over here, we know from our equation sheet, Q equals MC delta T. I call it MCAT, even though it's not an A. It looks like MCAT, and that's like a test people take that aren't teachers, right? Like MCAT, Q equals MCAT. So over here, I'm going to say the Q gained is going to be, who gains it? The water gains it. So this is the mass of the water times the specific heat of the water is equal to the change in temperature, which is T final minus T initial for the water. Equals the mass of the metal times that specific heat of the metal times the final minus initial. Okay? So far, so good? We clear on this? Once I'm here, I've got the numbers. Let's just plug it all in. But let's talk about where the numbers come from first. So mass of the water. How much was the mass of the water? It says I have 100 grams. We need to use kilograms, though. So that's going to be 0.1 kilograms of water. The specific heat of water is a known value. It's going to be given to us quite often. It's 4184. 4,184 joules per kilogram Kelvin. That's how much energy it takes to raise 1 kilogram of material by 1 Kelvin. Now, the change in temperature, this is where the specific heat problems get a little trickier. Here's why it gets tricky. The water's initial temperature, or final temperature, is 297 Kelvin. The initial temperature is 293. So that's pretty straightforward. We can do that math either in our head or on the whiteboard. 297 Kelvin minus 293 Kelvin. Okay, that's that. This is what's gained. All right, let's go see what's lost. The metal was 125 grams, so that's 0.125 kilograms times the specific heat. That's what I'm solving for. I'm solving for the specific heat, or C, of the metal. The change in temperature, its final temperature, same as the water, 297. Initial temperature was 310 Kelvin. I've got my expression. The only thing I don't know is my specific heat. I can go ahead and solve for all this. My change in temperature here is roughly 4 Kelvin. My change in temperature over here is 13, negative 13. This is a little weird. So we have to go back and look at our original equation, right? It's the Q gained equals the Q lost. No, Q gained equals negative Q lost. It has to be opposite because we know that the change in energy is zero. There's no outside work being done here. It's just a transfer of energy from one object to the next object. So these two things added together equals zero, which means they need to be equal but have opposite signs on them, and that takes care of that. All right? So if you go ahead, plug these numbers in, and you solve it, what you end up with is a C value that is really, really, really close to, let me see if we can find my answer. It's really close. It might be a little off, but it's really close to 900 joules per kilogram Kelvin. That means it takes 900 joules of energy to raise this sample, 1 kilogram of this sample by 1 degree Kelvin. That's what this means. And if I go to my textbook and I open my textbook and I say, what kinds of metals have specific heats of 900? What you would find is that this sample is actually aluminum. So this is a way that we can use heat transfer and this equation, this conservation of energy equation right here, we can use this to identify unknown materials. We probably did it in class. If you got questions, as always, drop in the comments, send me an email, ask me in class, okay? Till next time. See ya.